You have fallen into Event Horizon with John Michael Godier. John is joined today by Dr. Matthew Genge. Matthew Genge is a meteorite expert and lecturer in earth science and engineering at the Imperial College London. His research interests focus on meteoritics and planetary science and terrestrial igneous petrology. His work has encompassed the investigation and discovery of meteorites from Namibia to Antarctica.
Dr. Matthew Genge, welcome to the program.
Nice to be here.
Now, Doctor, we had the wonderful sample return mission, which promises so much from the asteroid Ryugu. And now that we have the samples back, it turns out that there was some contamination with one of the samples. Could you give us an overview of what happened with that particular sample?
So, we were very lucky to get one of the Ryugu samples. So we applied to Japanese Space Agency and they allocated us a sample. And we took great care with that sample. It was brought over to us in person. We took lots of precautions. And then the first time that I put the sample in the scanning electron microscope, I thought, what are these little fibers on the surface of the sample? And it turned out that they were microbes. So there were microbes on a space return sample. And I knew that the Japanese Space Agency, their curation facilities are fantastic. Almost no chance, very, very, very limited chance of contamination there. And so the question, of course, pops up in my mind immediately. Couldn't help it. Are these alien microbes? How do I investigate this? And anyway, so the story deepened. So we looked at the sample about a week later, and there were even more of them. They had bred. Were they going to take over the world? Who knew? And then about a month later, their numbers had decreased again. They started to die off. So we realized that that was consistent with these being good old terrestrial bacteria, that as soon as this sample had encountered the terrestrial environment, it got colonized by these bacteria who initially had a wonderful time eating all the organic material in Ryugu, and then eventually started to die off. And then just to, the proof of the pudding was we then repolished the sample, we re-prepared the sample, and they disappeared completely and never came back, showing that it was a chance event. One microbial spore or cell fell on that sample, and that was enough for it to become colonized.
But it also inadvertently demonstrated that a microbe from Earth can colonize something from space, right?
Absolutely. It shows that actually carbonaceous chondrites, these carbon-rich asteroids, they contain lots of goodies that microbes can eat. So microbes have evolved to be able to metabolize all sorts of organic molecules. They can live off of oil, and they can live off of all sorts of different hydrocarbons. And these molecules are present in these asteroids. Now, of course, on Earth, there's plenty of organic material around for microbes to eat, and only a very, very, very small portion of that falls from the sky. But on Mars, probably a large proportion of the organic material on Mars is stuff that falls as meteorites. So maybe on Mars, if there is microbial life, it's surviving on organics from space, or meteorite munchies, as I like to think of them.
Does this also indicate that in the history of Ryugu, it was never eaten? In other words, this is the first time it's encountered life?
That's much more difficult to say. There didn't seem to be any evidence for the microbes within the material itself. So once we repolished it, there was no evidence. And microbes actually fossilize really quickly. They actually fossilize themselves. So they can secrete minerals. And we know that can happen really quickly. So you can make these fossilized bacteria in 70 days or so. And there are none of these fossils within Ryugu. suggesting that no, there really aren't bacteria on Ryugu, and it hasn't ever encountered life.
But there are the building blocks of life, which gets into it being a gigantic carbonaceous chondrite. But I have a weird question for you, because one of your specialties is grains in space. Do you see a deposition of interplanetary grains that aren't actually native to that giant carbonaceous chondrite in the samples? In other words, is it getting hit by the same micrometeoroids that you collect in Antarctica?
That's a really good question. Yeah. So can we see little tiny dust-sized class within Ryugu? Well, actually, so Ryugu, the material, when you look at it, contains lots of little broken pieces. And that's because the asteroid has been battered to bits and it then reassembled under its own gravity. But most of the bits are clearly from the original asteroid. They're all like Ryugu. So we haven't found any exotic ones yet that are from outside Ryugu, but they're probably there. We do have evidence that Ryugu is bombarded by micrometeorites, these dust particles in space, because on the surface of some Ryugu grains, there's little impact pits, tiny little things that are tens of millionths of a meter across. And then there's this melted residue that's left on the surface where a micrometeorite has slammed into the surface, made an impact crater and vaporized, and then recondensed on the surface.
Now, carbonaceous chondrites are famous for such things as their chondrules, which are associated, at least with things like the Genge meteorite, with things like interstellar grains, pre-solar grains. What are those like, and do you see them in the Ryugu samples?
Well, it's always challenging to see pre-solar grains. You know, to find pre-solar grains, usually what you got to do is dissolve up a decent-sized piece of a meteorite, taking away everything except for those pre-solar grains. So we didn't do that to our sample. It was too precious. And I'm not absolutely sure whether anybody has identified pre-solar grains in Ryugu yet. They're almost certainly there because carbonaceous chondrites contain really abundant pre-solar grains, you know. Because we think carbonaceous chondrites formed in the outer solar system, material is less processed. So in the early solar system, those grains have been less heated, they've experienced less collisions, and they've survived for longer to be trapped within asteroids. And so, you know, those grains are nanodiamonds, they're graphite, silicon carbide. There's even silicate ones, but really you have to be able to see the isotopic anomalies, to see the strange isotopes that they contain in order to identify them.
Now, the strangeness of your Ryugu, as you mentioned, the carbonaceous chondrites probably originating way out in the outer solar system, almost certainly associated with comets. Is Ryugu potentially an extinct comet that's from way out there at some point that ended up nearby?
Yeah. So a lot of the research papers up until now have been about the distant origins of Ryugu. And that's largely based on the assumption that the further you go from the sun in the early solar system, the more primitive, the more carbon rich, the more like the composition of the sun the material will be. But that, to me, is rather a simplistic view of the early solar system. Because we know that there are some things in the solar system going on that mean it's not a simple, smooth change in conditions away from the sun. So, for example, Jupiter formed early and made a big gap in the nebula. It split the nebula into two. The inner nebula, which is where terrestrial planets formed, the ordinary chondrites formed, these chondrule-rich meteorites, and the outer solar system, which is carbon and water-rich. And when you start looking at actually the processes going on in the outer solar system, you've got Jupiter. It's kicking up lots of turbulence in the disk. Turbulence is really important because it starts throwing around things and concentrating things. And then beyond Jupiter, there's actually a pressure bump. There's an increase in pressure beyond Jupiter because what Jupiter is doing is it's pushing material outwards and everything else is trying to move inwards. And where the two meet, you get this enhancement of pressure in the pressure bump. So I think the pressure bump is probably where chondrules are forming in the outer solar system, because that's where millimeter-sized objects are being concentrated.
Are they still being formed?
Not now, because that was when the nebula was around, when you had all this gas. Now, without the gas, any dust particle in space is exposed to radiation from the sun. If they're really tiny, microns in size, they get pushed away from the sun by radiation pressure because photons of light, although they don't have any mass, they have momentum and they push things. But slightly larger particles, they're actually slowed down in their orbits by light. It's a really weird effect called Poynting-Robinson light drag, which sounds like it comes straight out of a science fiction novel. And it slows down the dust particles in their orbit. And Newton and Kepler are very, they specify exactly what happens to dust if you to an object if you slow it down in its orbit. It has to move inwards. And so those objects these dust particles spiral in towards the sun. So we can't keep dust around in the solar system for that long anymore. Millions of years, but it eventually falls into the sun.
Only, I guess, a residual, which is the zodiacal light, where you see the remnant, I guess.
Yeah.
But it wouldn't have been anything like what the early solar system would have looked like.
Absolutely. And of course, the zodiacal cloud is being produced all the time by collisions between objects, by comets. So it's actively being, if none of that happened, if there were no more collisions, eventually the zodiacal cloud would just disappear and it wouldn't be there anymore. But I guess my favorite thing about the zodiacal light is one of the few astronomical things that you can actually look up into the night sky and actually see it with the naked eye.
I have.
Yeah, it's incredible, isn't it?
Very occasionally, there it is, and it's the glinting of the sun off of interplanetary dust, and it's very fascinating to see. Now, when looking at the carbonaceous meteorites and asteroids like Ryugu, this tends to be very primitive material as opposed to like a chondrites where you see melting. Is there any evidence that Ryugu passed close enough to the sun to have any alteration to its geochemistry, or more importantly, melting water and minerals that might be associated with that?
So far nobody appears to have found any evidence for dehydration of clay minerals. So, clay minerals contain water in their atomic structure and a little bit that's absorbed onto them. So Ryugu contains about 9% water. That's a bit less than some TI chondrites, so it's a little less water rich. But interestingly, some of the phyllosilicates, some of the clay minerals, also contain ammonia. And that's one of the reasons why Ryugu why it's thought to may have formed at great distance from the sun, because ammonia ices might have been present.
And those volatiles, which starts looking something like comets, essentially.
And they would start looking like comets, absolutely. But then there are some things that don't make sense about this evidence. So, for example, one of the big pieces of evidence that has been used for Ryugu forming a great distance is that some of the minerals it contains are sulfides, and the sulfides form during aqueous alteration. So, we've accreted an asteroid containing ice. It heats up in the center because of the decay of short-lived radioisotopes like aluminium-26, melts that to make a more water reservoir, which then changes all the dry minerals into water-bearing minerals. So there's these sulfide minerals formed in aqueous alteration, and inside them are little bubbles that are CO2 rich. People have suggested that is evidence that Ryugu formed beyond the CO2 snow line, which is a long way from the sun. But I have a problem with this, because how does the CO2 stay around? Because CO2 ice that sublimates at a really, really low temperature. That CO2 then has to stay around until the ice melts, the water ice, to be trapped by the water, to be incorporated in these crystals that grew from water. So the evidence just that evidence really doesn't make sense. And I think I am somewhat uncomfortable with this very simple view that the solar system simply gets more primitive outwards.
Well, that's always a big question within science. You start simple and then you learn it's actually a lot more complex than you originally thought. And then you get a greater, better picture the more you learn. But you have to start simple, I suppose, right?
This is true. But the more we observe protoplanetary disks around other young stars, the more complex it's looking and the more variable it looks. A lot of things can happen to young stars that can create a lot of diversity. Hence the diversity we see within exoplanetary systems.
Yeah.
Which is great because it just makes the science more exciting.
Yeah, it makes it more interesting.
Wouldn't it be boring if it was all the same?
That would actually worry me if it were that. Now certain things are all the same. For example, the action of gravity and Newtonian orbits and all that we can understand. But although that gets complex, but that we can understand. But at the same time, the diversity of exoplanets and what can actually happen, I like the idea that it's much, much greater than what the representatives we have in this star system are.
Yeah.
We're going to see some very wild planet. Well, we already are, let's face it. And that's one of the exciting things about exoplanet research. Now, with Ryugu, there's also the question of amino acids. We've seen amino acids in carbonaceous chondrites like the Murchison meteorite and Allende again.
Oh, yeah.
Anything there? Did we see the building blocks of life all over?
Yes, there are amino acids in Ryugu. The one that springs off the top of my head is uracil. That's definitely present. So, the carbonaceous chondrites do contain a wide range of amino acids, including those that are used within living things. And of course, there's this hypothesis that the organic material for the terrestrial planets was delivered by some kind of late veneer, largely on the basis that the inner solar system, that material was dry and organic free, whereas the outer solar system material is carbon rich and water bearing.
Now, in regards to the sample, the contaminated sample, what did you learn about containment and how to avoid this in the future with future samples?
Well, very little, actually. Really, we prepared this sample in about the same way that we prepare meteorite samples of carbonaceous chondrites. Actually, we took more care with a Ryugu. We used a fresh polishing pad and deionized, sterilized water, and we took lots of precautions. And we very rarely see microbial contamination of carbonaceous chondrites. And the point is that really this contamination is very sporadic. You only need one cell to fall on it. But the chances of that happening are very low. And it did to us. We were the lucky ones whose sample got contaminated by microbes. But, produced a really interesting paper that really underlined that you can't use simply the occurrence of microbes in a space return sample. You can't use that as evidence for an extraterrestrial origin of those organisms. And actually, in the evidence, the study really says that the way we go about preparing samples is fine. You just have to expect that 1 in 100 of those samples or 1 in 1,000 of those samples will become contaminated by terrestrial microbes. And the thing about contamination is really only a problem if it interferes with the analyses that you are doing. So I was looking at the minerals and the chemical compositions of those minerals, not the organics, not the isotopes. So I didn't really have to worry about this contamination of microbes.
It has to be said, you may not have gotten as lucky as the contaminating microbe, because if one single microbe finds a food source of that magnitude to where it can form a detectable colony, it hit the jackpot, at least until the food runs out.
Yes, I think the food didn't run out. We were not very nice to these microbes because we kept putting the sample in the scanning electron microscope under a pretty high vacuum and then bombarding it with electrons at 20 keV, which apparently they don't like.
Yeah, maybe it didn't get so lucky. But you could say that anyone that finds a meteorite on Earth that we haven't found would get lucky. at least for a time, except maybe in Antarctica. And I know you do a lot of work there with micrometeoroids. What's that like as far as contamination? Do you see it down there, or is it a fairly sterile environment where the chances get even lower for contamination? I know that a lot of the meteorites found there fell thousands of years ago on the glacier and collect up, and they're basically pristine, a lot of them.
Yeah, so I've been to Antarctica twice now collecting meteorites and cosmic dust. And there is certainly the potential for contamination. So there, even high up in the transantarctic mountains down near pole, you find some evidence for melting of water ice. You get the thermal island effect, and at certain, on certain days, you generate some transient water. That gets worse and worse as you head towards the coast. And of course, wherever you have water, there's the potential to have living things. Even a long way from pole, very occasionally, you find the odd dead skewer that's managed to fly inland or get blown inland. So there's still a possibility of contamination, but it's much, much less than, say, a desert meteorite find.
So what's it look like collecting micrometeoroids at Antarctica? I mean, what do you do? Do you just take a sample in an area where a glacier is sort of congregating and melting out, and then melt it and look for, grab a magnet and try to...
It's so ridiculously easy, you wouldn't believe it. You basically take a bag and you shovel dust-sized sediment into that bag that you find in a moraine, and it contains an unbelievably large proportion of micrometeorites. So I had about a kilogram bag, and I've got over 3,000 micrometeorites out of that kilogram bag so far, and there's plenty more still to go. It's much easier than for example, collecting micrometeorites on rooftops, where you have to look through an awful lot of material in order to find any.
Now, if somebody were to do that, and I remember there was an experiment that was published, I believe, in Sky and Telescope magazine back in the 1980s when I was first learning about astronomy as a little kid. Not so little. They had an experiment where you could collect with a magnet potential micrometeoroids off of roofs. You kind of put out a pan of water or whatever, and anything that you see in there might be. So drag a magnet. What proportion of that would actually be micrometeoroids?
So there's a guy, John Larson, who is a Norwegian jazz musician, or used to be, and he regularly collects micrometeorites on rooftops. So he went through about 500 kilograms and found 50 micrometeorites. So they are there, but in relatively low abundances. Now, I think actually the abundance is much higher than that, but they are very difficult to spot because you have lots of other spherules there. So every time you drill, you make lots of spherules. You get spherules dropping out of the atmosphere from coal smelters and diesel engines. And so there's lots and lots of metallic spherules. Fireworks, apparently, are a really big source of spherules. You get all these bizarre compositions. So you really need to look at their compositions, and you really need to know what micrometeorites look like. So I know in the US, Scott Peterson has been collecting an awful lot of micrometeorites from huge numbers, from mainly on rooftops, but he's even dredged them out of the Great Lakes, dragging a magnet through the sediment. So they are around. They fall all around us.
It's a constant rain, and I mean, you can see it sometimes with ones that are falling as meteors, but do the ones that you find actually do that, or do they just sprinkle down slowly? What preserves them and keeps them from vaporizing?
So the majority of micrometeorites were dust-sized particles in space. And it's quite easy to say why that's the case, because the dust flux is maybe 40,000 tons per year, whereas meteorites is about 100 tons. So even if you vaporize all those meteorites, a drop in the ocean. And the reason that micrometeorites actually survive, these tiny little particles survive, whereas meteorites have this blazing passage through the atmosphere, is these really low mass particles are slowed down very quickly by the atmosphere at very high altitude, a long way above so meteorites typically, they're reaching their peak deceleration at maybe 40 kilometers altitude. Whereas micrometeorites, it's above 80. And that means that they are encountering very diffuse atmosphere, very low density atmosphere. So they're more gently slowed. And that gives them more opportunity to lose heat. It's all about losing heat. If you lose enough heat, you get through the atmosphere.
Do they form as they filter down? Do they affect the Earth's weather? In other words, can raindrops and things like hail form around a dropping micrometeoroid?
Well, certainly in the stratosphere and certainly in the troposphere, there is the vast majority of dust is terrestrial. Stratosphere, there's a bit more micrometeorites, but most of the cloud nuclei are going to form on things like volcanic aerosols. They vastly outnumber micrometeorites. But in the mesosphere, up there, because it's really difficult to convect stuff up through the top of the stratosphere, in the mesosphere, most of the dust is either come from space or it's recondensed from those micrometeorites that have burnt up during atmospheric entry. But of course, mesospheric clouds don't have an awful lot of effect on the climate.
What do the composition of the spherules look like? I mean, how carbonaceous are they versus chondritic in their general makeup?
So we can really only tell confidently from the ones that are unmelted. So in the unmelted ones, the smaller ones, so maybe below 200 microns across, are absolutely dominated by carbon-rich, carbonaceous chondrite-like materials. Whereas the larger ones, they look more like ordinary chondrites. So there's a change with the size of particles. Amongst the faster ones that enter the atmosphere, they completely melt. And we can tell something about where they come from. And again, it looks like the majority of those come from carbonaceous chondrites, the small ones. And the larger ones are ordinary chondrites.
It's interesting because that sort of goes backwards with the meteorites. So you don't find large carbonaceous chondrites all that often. They're not that rare, but you don't find them all that often as compared to like a L6 chondrite, where they're everywhere.
Well, they're tougher.
Indeed, right? Yeah,
they're absolutely tougher. But then with the one there was a paper quite a few years ago about during impacts on asteroids, carbonaceous chondrites tend to produce very fine dust because they explosively dehydrate. So think about all that water stored in the clay minerals. You vaporize it and it turns into steam, and you can generate lots of really fine dust.
That'd be fascinating to actually have a spacecraft out there, like, Hayabusa or one of them, just looking at it when it gets hit by something. And you have that sort of momentary outgassing of volatiles, water and things like that. I mean, that would be beyond lucky, but still.
Well, or we can drop a projectile into it.
We've done that too. And
we've done that too.
Yeah. Twice.
Dart?
Yeah. And Deep Impact, remember that one?
Yeah.
And I'm sure we're going to do more of that because that's a great way to learn something about although I want an in situ robotic geologist, if we could actually get one to actually sit there on the surface of one of these things and look at that fresh.
Why send a robot when you can send a geologist?
And that's where we're going to go next as far as humans and asteroids and asteroid mining. What are the advantages right now, economically speaking, to start looking at asteroid mining, if any?
So you're right. It all depends on the economics, because as we all know, anything people can make money from generally happens. And at the moment, that's a challenge with asteroids. So even though asteroids contain lots of things that are useful, that are resources, they are not economic to exploit because of the cost of space missions. So even with launch costs coming down dramatically, thanks to commercial entities, it's still very expensive to do planetary missions. And asteroids, some of them are dynamically more easy to get to than the moon, but it's still pretty expensive to get to the moon. And remember, in particular for a commercial operation, you need investment, and investors want to see a return on their money within a certain period. They don't want to wait 5 years for that spacecraft to get there and bring the stuff back. They want that money as soon as possible. So I think at present, asteroid mining is not going to happen, except as a support industry for government-led space agencies. So all of the space agencies, NASA, ESA, Japanese Space Agency, Chinese Space Agency, they are all looking into in situ resource utilization, which is supporting that mission with locally obtained materials. If you don't need to take the fuel with you to fly back from the asteroid, if you can make it there, you can save yourself an awful lot of money.
In other words, if you need to make an I-beam and you're already going to be in space, why not make it out of an asteroid if you can?
Yes.
And I guess that's,
exactly.
Again, infrastructure support. But as commercial space exploration continues, which it seems like it's going to, then they too may make use of it. If they want to build a hotel in solar orbit or something like that, then why not do it out of an asteroid instead of launching steel from the planet? Do you see that privately happening?
Well, again, it depends on the economics. How much can you make out of a hotel that's in Earth orbit? I suppose billions, because there are people with that kind of money who'd be willing to pay that to stay up there. I really think that this is going to happen slowly. It will happen initially through commercial enterprises supporting space agencies. And then once that ecosystem, that business ecosystem exists, then prices start coming down. And then it becomes economic to actually extract resources from asteroids. And, there are an enormous amount of resources out there. So asteroid 16 Psyche is just one huge lump of metal. What is that? Over 100 kilometers long. And it's iron, nickel, cobalt, metal.
And we have a mission going there, so we'll really get a characterization of that asteroid, which sort of one of the reasons it's going there is to look at a metallic asteroid just to find out.
Well, let's hope it gets there and it is a metallic asteroid.
Yeah, absolutely. I don't know what else it could be, but...
Well, it's got... Some M-types have got a water stretching band in their infrared spectrum.
Oh, really?
Yeah. Now, whether that's, carbonaceous chondrite dust sprinkled over the top, who knows? Because what we learned with Ryugu, you might remember when JAXA arrived at Ryugu, there was this shock because the infrared spectrum really didn't show much of a water absorption band. And the initial interpretation was we've come all the way to carbonaceous chondrite and it's metamorphosed and it's lost all its water. And it turned, and of course, that happened right up until the samples came back. We thought that. In fact, I have colleagues who have planned research projects to answer the question, why was Ryugu heated? And the samples come back and they're not heated. And it was because the very surface of Ryugu, the upper, less than a micron, has experienced dehydration because of impacts.
Less than a micron. That's amazing. But that whole thing was amazing. That whole thing, I can't say enough good things about JAXA because they are very bold. Probably the boldest space agency. They will take risks.
They are.
And this paid off because they got their sample and some. There was extra material, as I recall, in there. So it couldn't have worked out better. Now, what is the future of asteroid sample returns? Who else has plans for further work in this?
Oh, that's a very good question. So I don't think JAXA's got anything on the books right now, or NASA or ESA. So I don't think there are any plans. But missions get suggested all the time, and there are so many different asteroids for us to look at. So I have heard suggestions because the way mission proposals work is they go through various stages before they get selected. So people are putting together. We've seen talks on sampling Phobos and Deimos, which are P and D type asteroids. That would be absolutely fascinating. Also, then really another cool reason for doing it is there is likely to be samples from Mars on Phobos and Deimos that were blasted off the surface of Mars early, and so we can also sample the Martian surface without actually bothering to land on Mars, which is quite cool. But there are plenty of asteroids up there. We'd love to have a sample of an M type too, and some of the E types. There's a whole question about, is Vista the only big basaltic asteroid? V types are very interesting too. Not V types. Some of the C types have been linked to the Uralites. The C type asteroids have been related to the Uralites. And the Uralites are such weird meteorites. We'd really like to know what their asteroids look like. Are they really a disrupted protoplanet? Some of the diamonds in Uralites have inclusions within them that have been suggested to form a quite high pressure.
I seem to remember, and correct me if I'm wrong on this, but I seem to remember, we know that Vesta is the parent body of a number of chondrite meteorites. We know that, or we've established it pretty well that these meteorites came from that asteroid. But I remember with the Uralites, I think some people were saying possibly Mercury. Do you remember that?
Well, Mercury gets pulled out as a potential source for anything weird. Whereas, actually the surface of Mercury, the spectroscopy of Mercury looks much more like the entitite chondrites. You've even got hints of things like oldamite there, these weird magnesium sulfides like niningirite, and oldamite, which is a calcium sulfide. So, yeah, I expect rocks from Mercury do look very weird, but I don't think they look like Uralites packed full of carbon.
Yeah, but the enstatites are interesting in themselves. Those are weird rocks too, has to be said.
They are, and supposedly they have a composition closest to the Earth. I've never quite got my head around how we actually know that, because the Earth's composition is a bit of an estimate anyway, that's based on meteorites.
Yeah, it's hard to say, and there are a lot of oddball in the history of recent planetary science that we know that Earth was hit, or proto-Earth was hit by Theia, and that, the moon, the material that coalesced in the moon was thrown off, and maybe pieces of Theia are preserved deep in the interior of the Earth. But there was also the idea that Theia might actually have been Mercury, and it's the reason that Mercury is mostly a metallic core instead of having much of a mantle, and that it might dynamically have been possible for it to be Theia, and it's what's left after the glancing blow, which might explain why it looks a little bit like Earth.
Yeah,
geologically anyway.
Well,
kind of a stretch, but it's an interesting thought.
Well, I think if you shuffle numbers around enough with a lot of modeling, you make certain assumptions, and the outcomes of the model are highly dependent on the assumptions. So you can prove just about anything using a numerical model.
That's certainly true. So what's on the agenda for the future, especially with Antarctica? Are you going to make a third trip, and what's it like to have to do science in Antarctica and live down there for a time?
So I would love to go back to Antarctica. So I've been twice. I need to talk to my boss about it because it's rather awkward, and it lands right in the middle of 2 terms. So teaching is always a problem. But one of the reasons I would love to go back is Antarctica is just this incredible place that's very different from anywhere else on Earth. It's very, very white, blue, and black. Very few other colors in Antarctica, and it's such a dramatic place to work in. I would spend hours and hours just sitting outside the tent looking at the scenery, because it was just so amazing. All these sastrugi, these snow dunes blowing across this amazing deep blue high pressure ice. And it's actually, we camped, and it's the nicest camping I have ever done, because there is no rain, there are no insects. You can eat 4,000 calories a day and not put on weight. And the tent is always warm because you keep it warm. I was never cold in Antarctica, because if you are cold in Antarctica, you are in serious trouble because you lose so much heat.
Soon to go to sleep.
Yes, and soon to go to sleep. Yeah.
Ultimately. Yeah, so if you start feeling tired in Antarctica and you're out and about, you're in trouble. But it's not long before you don't know that. And that's it.
Well, yeah, I always tell myself I am a geologist, really, by training, as well as being a planetary scientist. So I teach geologists. So I take students into the big outdoors, places like northwest Scotland, and we climb mountains. And so I always tell students when they're cold, have a chocolate bar and run around for a bit, and you'll be as warm as anything. They don't listen to me. It's the same in Antarctica. Stay active, keep eating, you won't freeze.
Did you, as a geologist, get any time or opportunity to just walk over and pick up a rock and look at the geology of Antarctica if you were, if there was an exposure, of the black rock? Did you get a chance to run over and take a look? And what'd you find?
Oh, yeah. So there was one day at Larkman Nunatak. So I went with the US Antarctic program with an expedition called ANSMET, Antarctic Search for Meteorites. So we're out in the field looking for meteorites, and we're foot searching on a moraine, which can be a bit tedious because you find all these little 1 centimeter sized meteorites that are blown along the surface of the ice and pitched up in the moraine. Anyway, so we're looking for these, and then all of a sudden somebody finds this amazing fern fossil. And all of a sudden, it was funny because, we've been looking for meteorites for about a month. And all of a sudden, without anybody saying it, it turned from looking for meteorites into looking for fossils. And Antarctica is incredible. And it really, when it comes for things like fossils, because it really shows you that in the rest of the world has been picked clean of really nice fossils. And the rest of the world used to be like Antarctica. There were great fossils just knocking around everywhere, and they've all been picked up.
And it also, I think one of the things, should I ever visit Antarctica, and I don't really have a reason to do that, but should I ever visit it, make a film or something and get permission, I think the thing that would stick most in my mind is thinking about what that place was once like before, continental drift brought it where it is and it froze over. But those fern fossils just sort of give you an idea of what this once was and how it was once tropical. And I think that the idea of an entire continent going from tropical to what it is now is absolutely amazing and poignant, right?
No, absolutely. But, even during the Cretaceous, Antarctica was fairly close to the pole. It was just a much warmer climate. It was 8 degrees warmer than the Cretaceous thermal maximum, which actually makes current estimates of going up by 2.5 degrees really scary. That's a significant proportion of the highest temperatures the Earth has ever had.
And it pays to remember there were once dinosaurs there, and underneath that ice, you can just imagine the fossils. All right, Doctor, thank you for joining us today. It was a wonderful conversation. I wish you great luck with your micrometeoroid research and continued research with Ryugu and the samples. And I can't wait to see what else is found about these asteroids and carbonaceous chondrites.
Thank you.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.